Greetings and welcome, friends. Mr. Waddy here. We've been going over section 8.1 and 8.2, which is the idea of graphing quadratic equations of the form x squared plus c, or y equals x squared plus c, and more recently, a section that I called steeper slopes, although sometimes they're smooster slopes. Schmooster. Man, schmooster sounds like it would be an awesome name for a cell phone app. Yes, absolutely. Where you like kiss your phone and then like it gives you data. That would be weird. Also very germy. I don't recommend kissing your phone. But anyway, Schmooster, copyright Brian Waddy, 2017. We're going over some of our homework problems with these steeper slope situations. And here we go. Here we go. So let's see. Graph the equation. Compare it to f of x equals x squared. So first of all, the first thing we should do is figure out where the vertex is. Notice this is a plus 0. So the vertex is 0, 0. So I'm going to plot that point right here. Plot it. And the number in front of the x squared is 1/4. And our normal slopes, just like slope-intercept form for lines, came from... right, the m in front of our x term, our quote-unquote slopes for quadratics comes from the number in front of the squared term. Now, our normal slopes are up 1, over 1, up 3, over 1, up 5, over 1, where these numerators were the consecutive odd numbers, 1, 3, 5, 7, 9, 11, 13, 15, 17, 19, 21, 23, etc. But now that I've got this number out front, it's going to schmoosh my graph. I've been schmooshed. So what I do is I multiply just the numerator by 1/4. So 1/4 times that. Nope, I just wrote a 3. That 3 is not the same as a 4. We're learning math all the time. Isn't it great? 3s and 4s are different. And so I multiply each of those by 1/4. And I'm not going to reduce the entire fraction, but 1/4 times 1 will be 1. No. I'm leaving it in terms of fractions, though. 1/4 over 1. 1/4 times 3 will be 3/4 over 1, or 3/4 over 1. And 5/4 will be 5/4 over 1. And so these numerators are going to be the amount that my rise is, my up is, and my denominator is going to be my run, which is always 1 for the way these go. Now, I'm going up 1/4. Now notice here's 2. Let's see. Let's look at some tick marks here. Here is 1. Here is 1/2 and 1.5. Because these are fourths, I'm going to want my y-axis to be measured in fourths. Okay, that's what I'm wanting to do. So I'm going to actually add some tick marks. Halfway between 1/2 is 1/4, right? There's 3/4. There's 1 1/4, 1 1/2, 1 3/4, 2 1/4, 2 1/2, 2 3/4, 3. Let's see. I don't like where that one landed. Right, there's 3. There's 3 1/2. 3 3/4. Right, so I add some tick marks so that between the entire units, the whole numbers, I'm going to have 4 spaces or 3 lines. Okay, and those are now quarter marks. So my first point is going to be found by going up 1/4 and over 1. And notice my x-axis is still counting normally. Those are all the 1s. So up 1 of these quarter tick marks and over 1. Now I'm going to go up 3 of these quarter tick marks. So 1, 2, 3 of these quarter tick marks and over 1. And then I'm going to go up 5 of these quarter tick marks. So that's going to be 1, 2, 3, 4, bringing me up to the 2 1/4 mark and over 1. All right, so kind of weird, especially with these fractions, but by adding these tick marks at the fourths places, it's so much easier to graph. Yeah, and I can now mirror these over, up a quarter, backwards 1, up 3/4, backwards 1, and up 5/4, backwards 1. And now I'm going to draw the best parabola that I can, and I find that I can draw downward-facing parabolas easier. So I'm going to rotate my paper. Yeah, so you just draw as best you can. Yeah. Yeah, it technically doesn't come to a sharp point. It's a curve there. But the points are what matter to me more than are what matter to me more than your ability to draw a curve or to rotate a canvas effectively. So there we go. There's our parabola. Right? So it's a little bit tricky because of these fourths. The next one will I chose one of the more difficult problems here, but let's look at one where the vertex is at a different place. So here's question 10 from the same assignment. So this +1 is going to be vertical shift up 1, so that's my vertex at 0, 1. So let's see, what are we counting by? Oh, here we go. So 0, 1 would be right here by the looks of things. And the slopes are going to be determined by this -3. Okay, so my normal slopes are the odd numbers. They're so peculiar, they're a mystery to me. They are odd. So up 1 over 1, up 3 over 1, up 5, and I'm leaving a weird space right here on purpose, over 1. I could even think of up 7 over 1. ... Well, we're not. This is my normal slopes for a parabola, and now I'm going to multiply the numerators only by -3. And right, that's going to be an upside down parabola because of that. Good call. So let's simplify these numerators. -3 times 1 is now going to be down 3 over 1. -3 times 3 is the same as -9, so that's down 9 over 1. And then down 15 over 1. You're getting this, Tyler, right? Down 21 over 1, like so. And so what I've done is just multiply the odd numbers by the -3, and that gives me my quote-unquote slopes, because these are not technically the slopes of the slope of a parabola would be the instantaneous, the tangent line to any given point on a parabola. But don't worry about that. That's a calculus concept. So let's see. From this point, let's go down 3 and over 1. Plot a point. And this is so much easier than making a table of values. Let's see. Down 9 over 1. Okay, so down 1, 2, 3, 4. That's going to bring me to -11. Is that right? That was at negative. Yeah. Over 1. Yeah. Well, it's a vertical stretch because of the 3 there. The previous one was a smoosh vertically. And then I would technically go down -15 over 1, but that's super far down. So let's see, let's mirror these points over the axis of symmetry. The axis of symmetry is the vertical line, in this case, that passes through the vertex, the kind of highest point in this case, whereas sometimes on a parabola it can be the lowest point. Sometimes it's referred to as the turning point, where it was going uphill and then it starts going downhill. So I mirror these points like so. And let's draw a parabola. It's a steep, steep parabola. And you believe it. All right. And so this -3, just in terms of some terminology, this parabola, I would say, opens down. Specifically because of that negative there. All right. It was also a vertical stretch. Vertical, all right, vertical stretch by 3. And the +1 also was a vertical shift up 1. If you want to think about this in terms of transformations. But yeah, if you know the slopes and you know your starting point, which is your vertex, it's not bad. So the vertex is the tallest point on this downward opening parabola. Let's check out another one. Last one, I think. Ooh, 23. Now it says find the zeros of the function. The zeros are going to be just a number, numbers in this case, I guess, that are the x coordinates or coordinates of our vertex, of our, parabola. Man, words tricking me today. All right, so the vertex here is going to be this negative 16. So 0, negative 16 is where this starts. Let's plot that point. Oh, man. Let me see if I can find a better graph for me. All right, I want to like try to make a graph where I can actually see what's going on. Let's see, what was this, number 23? Let's see, let's invert colors. Ready? Whoop, 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 whoop. I just want to make a larger... will I end up seeing these? All right. No. Still working on it, friends. Here we go. Let's zoom. Enhance. Can you enhance right there, computer? Enhance. Oh dear. Things are like bogging down on me like crazy. Well, let's oh, there it goes. Well, there we go. All right, not much better, but I can see at least a little bit more of those lines. That's all I was trying to go for. So the vertex is at 0, negative 16, which I barely fit in here. Barely. And the slopes of this parabola, the sloppy slopes, normally would have been up 1 over 1, up 3 over 1, up 5 over 1. And I need to see this work, mind you, if you want credit on a mini quiz or on a test, if you're using my technique. Otherwise, you're going to have to make like a whole table of values. But don't waste your time making tables when you can think about the graph. All right. So multiply all of those by 4, the number in front of the x squared, which is going to stretch this parabola vertically. So up 4 over 1. Yeah, we've got that point. Yep, we've already plotted that. Up 12 over 1, and then up 4 times 5 is 20 over 1. So from negative 16 going up 4 is going to bring me to the negative 12 spot and over 1. Then going up 12 from negative 12, oh, that's going to bring me all the way to 0. That's convenient. Over 1. And then going up 20 from there, hey, it's almost like I planned this coordinate plane for us perfectly. Over 1. Right, so I went up 4, up 12, and then up 20 for my quote-unquote slopes. And then let's mirror those. Mirror on the wall. Who's the greatest parabola drawer of all? All right, let's rotate this canvas. Here we go. Tip your world upside down with these parabolas, friend. Look out. No. Try again. Not bad, not bad. All right, sound effects are necessary, and also I recommend when you're drawing to just like stick your tongue out of the corner of your mouth just a little bit. It allows you to focus. That's what I did in elementary school when I would doodle. So the question was, what are the zeros of this graph? And the zeros are going to be the x coordinates, or x-intercepts, x coordinates. So the zeros occur at positive 2 and negative 2. So I could actually write plus or minus 2 if you want to be cool. You could save yourself writing a number, maybe. But there you go. So those are the zeros. Thanks for watching, internet friends.